function of distance from a heat source. You know when you're at those restaurants outside and they have those little space heater things, and the further you get away from them, the cooler you are, right?
Yeah.
I could say that my temperature is a function of my distance from that heat source. Okay?
I got it.
Let's just say I'm measuring my temperature in degrees Celsius. We'll be scientific about this. And distance, we can say, I don't know, I guess I should say meters.
Keep it metric. Absolutely. Right.
Okay? So, I always like, whenever I'm doing these meetings, I like to get a sense of what is where, what the function might look like. So if temperature is a function of distance, my temperature is going to be here, degrees Celsius. My distance is going to be here, in meters. Just a very quick sketch. I'm thinking that as I move away, my temperature is going to get quickly colder, but then look something like that. How are we doing so far?
That sounds great.
Fantastic. All right, so let's just do some interpreting. If I had something like this, f of 5 equals 5. Okay? So, let's just figure out what this means. Okay, that 5 is my distance. So what that means is when I'm 5 feet from my heat
or
source,
meters in this case.
5 meters.
Yes,
thank
right.
you. Okay, when you are 5 meters from the heat source, the temperature is 12 degrees. That seems pretty straightforward.
I got it.
So good? All right, so now let's throw some derivatives in there. Remember, derivative is slope. So let's stick with our 5. And I don't know. How about that? So remember, derivative is your slope if you're talking graphically. It's also your rate of change. So what's changing here? Well, my temperature is changing as my distance is changing. Okay? Change in y over change in x. So the 5 is still my meters. So at 5 meters from my heat source. Now, what is that negative 2 representing?
Well, that's the slope, right? I mean, a derivative is just a slope or rate of change.
It's the change. Right. So that means that my temperature is decreasing at a rate of 2 degrees per
Right.
year.
I always think if you can come up with the units, that's really the key there. And the units, of course, is just change in y, which is in this case temperature in degrees Celsius, over change in x, which in this case is distance in meters. So of course it's just degrees Celsius per meter.
Perfect.
Right? So at 5 meters from the heat, the temperature is decreasing at a rate of 2 degrees per meter.
Beautiful.
Degrees Celsius per meter. Beautiful.
Yeah.
I love it.
And you know what you said, Mr. Haas, is totally perfect. Whenever you're doing these, think of your units. Slope, change of y over change of x. So your derivative is always going to be your degrees per meter. And that really helps you
It's
get
the
meter.
slope. Degrees per meter. Got it.
Slope. Great.
Hey, let's take a look at the second derivative.
Let's do that.
Yeah. Well, sure.
Okay.
So the first derivative is obviously negative because this thing has a negative slope.
Right.
The second derivative, though, I noticed that the way you drew this, and you know, if we gave a problem in class, we'd have to give you a little bit more information. We're just kind of making things up here. But
right.
The way you drew this, it's concave up, which means the second derivative would have to be positive.
It sure
right?
would. So I'm just throwing in a number there. Okay? Yeah, so my second derivative has to be positive, as you said, because it's concave up. So let's try to figure out what this means in the context of this story, or this situation. All right, well, this part never changes. At 5 meters. And I like saying at 5 meters because that means it's right at that instant. Remember, we're all about instantaneous rate. At 5 meters, now this is when it gets a little kooky, right? The second derivative is the rate of the rate.
Right, or it tells me how the rate is changing.
It tells me how the rate is changing, okay? So at 5 meters, the temperature, right? The temperature is decreasing. The rate, let's start off.
Yeah,
The
let's say
rate
the rate.
at which the temperature is decreasing is increasing by 1 degree per meter each meter.
So can I say it
Yeah,
again? So
please
so
do. I'll
another
write it and say
yes, sure. So let me just give this. So you wrote 1 there, which means presumably maybe at 4 meters the temperature was dropping by, I don't know, if you make up some number or something.
Right.
At 4 meters it was dropping by 6 degrees per meter.
Right.
But now a meter later it's dropping by 1 degree less per meter, so it's only dropping by 5 degrees per meter. And then maybe the next meter it'll only drop by 4 degrees per meter. Of
Exactly
course,
right.
the rate at which the rate is changing is also changing. We only know what's happening at 5 meters. So let me read what you have there, see if this makes any
at
sense.
5 meters, the rate at which the temperature is decreasing is increasing by 1 degree.
Yeah, that makes sense. So
Per
every
meter.
meter, it's the temperature is still decreasing, but the rate at which it's decreasing is slowing.
Yeah.
I gotcha.
Yeah, exactly right. And if you're looking at this, it makes sense. Whoa, my temperature is really dropping, but it's dropping less by less and less and less. The rate at which it's dropping is less, dramatic, if you will.
Yeah, I mean, it's a little funny to say, but I think it makes total sense, Mr. Ray.
Fantastic.
Thank you.
All right?
So we got a little example from biology class. Mr.
Wonderful.
Yeah. This says calories is a function of weight. Now, I just wrote the basics on the board. Really what I'm trying to say here is the amount of calories that an animal needs is a function of its weight.
That makes sense?
Which makes sense. So like a little bitty mouse probably needs less calories than a whale.
I would think so,
I
yes.
probably
Yeah.
think. A
I'm
whale
thinking
probably
so
eat a
too.
bunch of mice. If it,
Yeah.
I mean, I'm sure I think they're vegetarian. Well,
Yeah.
some are. Okay, so I'm going to draw a little picture of this here. So calories is a function of weight. I'm going to write it in function notation if that's okay.
Let's do it.
Calories is a function of weight. The guy in parentheses is always the x value. Do you do that always? You know.
Yeah, absolutely.
And I'm just going to make up units. Let's say this is pounds, and let's say calories. Well, I think that is
Calories
a unit.
is
Well,
calories.
This is like the amount of food, I suppose,
Very good.
and the unit is calories.
Good. So we're talking about the amount of food that a creature needs to support itself.
That's what I'm saying.
Very good.
The amount of food that something needs depends on its weight.
Good.
So that a creature needs, right? So, do you know how this is going to look? Actually, this is kind of an interesting one.
Yeah, I think it's going to be, obviously as a creature gets bigger, it needs
Yeah.
more food, but I'm pretty sure it's concave down.
It is.
So I know, they say little birds eat at their body weight,
They do.
and
yeah.
elephants eat a lot
No,
less
than their body weight.
than their
which is-
body
which
weight.
is good news.
Which is good
I
news.
don't know. But yeah, so as an animal's weight goes up, they certainly need more calories, but the rate at which the calories are increasing is decreasing at a decreasing rate.
Very nice.
So let's just go over sort of the basics here. Like, what would it mean? I'll just make up a few things. What would it mean if I wrote, I guess we're using 5. I'm going to use this. 2. How about that?
Okay, so
S
something.
of 2 equals 1.
All right.
Yeah.
Ah.
So what am I saying here, really?
Well, I guess a creature that weighs 2 pounds needs to consume 1 calorie.
That's exactly what I'm saying. If you weigh 2 pounds, you need 1 calorie. Should I write that down?
Sure.
I don't know.
Oh, no,
Want me
you
to
don't
write
need
that
to.
down?
No, we don't need to write that
Hey,
down.
if you weigh
Okay,
2 pounds, you need 1 calorie.
beautiful. We're
Now,
rolling.
calorie per day, who knows? I
Who
mean,
knows,
this is,
right.
we're making up units, but that could be reasonable.
Yeah.
So let's do a derivative now.
Okay, very exciting.
Okay, this is again for my 2-pound critter.
Okay.
You think of any animals that weigh 2 pounds?
You
How about a
know,
weasel?
a
What
weasel
do they
probably
weigh?
weighs 2 pounds.
I really don't
Some of
know.
those little toy poodles weigh like 2 pounds.
Yeah, perhaps. I don't know. I'm going to put 0.5 for this.
Mm.
So this one I'm going to write down. And as you said, I always like to, this is what's happening at 2 pounds.
Mm-hmm.
So this is my critter who's at 2 pounds.
That's the weight of your critter.
Yeah. At 2 pounds, this is a positive number, so it's telling me that the calories are increasing. And it's telling me that the rate at which the calories are increasing are half a pound per, oh sorry, half a calorie per pound.
You got it.
Did we do the last one right?
We did.
Okay.
Yeah.
So at 2 pounds, I'm going to say caloric intake is increasing. How about that? Or how about if I just say calories increasing?
Okay.
Calorie requirements are increasing by 0.5 calories. That seems a little bit crazy, but
That's all right. Per
per pound.
pound.
Does that seem like that's
We're just making up numbers.
Insane thing? Half a calorie? It's like nothing.
Well, we're just making up numbers. But the idea is that the derivative is the slope. It's the change. So at that moment, when a creature is 2 pounds,
His calorie requirement is increasing at a rate of half a calorie. So in other words, a 3-pound creature only needs half a calorie more?
Well,
That's insane.
well, we're kind of at a different point there at the 3 pounds, but
Anyway.
anyway.
But all right, perhaps that's possible. All right, let's just do the last one.
We're not
here.
biologists.
Let's do the second derivative.
Okay.
Well, ooh, interesting.
Ah,
It's concave down. So what
okay.
does that tell me?
That means it's got to be negative.
Yeah, some kind of negative. And you want to make up a better number than I had? My number was insane
Me?
there.
No. I'm just going to make up something random. How about
All right.
-6?
-6, excellent.
We're
And
talking
you-
about a little
You
creature
students taking
here.
biology, don't report us to your biology.
Please don't.
Because this is bad. All right.
Okay.
So this is telling me how the rate is changing. It's the change in the rate of calorie increase. And it's actually decreasing.
Yeah.
So what should I say? At 2 pounds, the caloric, the rate, I'm going to
The
change
rate,
this to
yeah.
rate. How about this? The rate of caloric increase is decreasing. Wait, increase, decrease, this is crazy. Decreasing by 6, and what are the units?
Calories per pound per pound. Or
Really
you
per
can say
pound,
per
each
pound or each pound. I usually do like an each pound at the end so it doesn't get ridiculous.
Yeah, I mean, I'm writing it a little bit funny, but let's see if this makes sense at least what I'm saying. So this is a 2-pound critter. Yes, his calorie intake is increasing, but it increased by 6 calories less than the critter who was only 1 pound. I'm making it, these numbers are ridiculous.
Sure.
Now that I think about this story.
But that's all right. We like being
But
ridiculous
the
from time to
rate of
time.
increase is decreasing. Increasing at a decreasing rate.
I think that's clear. Yeah. The calories that you need are increasing at a decreasing rate. Beautiful. I love it.